Essentially what we learned on, I guess, Wednesday of last week is that the function y equals f of x, since it can be transformed for any function using a, b, h, and k, if f of x happens to be equal to root x, we can certainly transform it. And if you apply y equals a f of b bracket x minus h n bracket m bracket plus k, where the argument is b times x minus h, the argument of the function is what follows f in the function notation, then this transformed function becomes y equals a multiplied by the square root of b times x minus h. So that's the argument plus k. And then we talked about the fact that you need to know what root x looks like. I guess it's half of a sideways parabola. I think I have a picture of one here rather than me drawing it. Yep. F of x equals root x is the blue function in this question. So basically we were looking at applying transformations to that function to determine properties of new functions. Take a look at your work, please. Does anybody have any questions you would like me to go over here? Lynette.
Question 10.
Okay, let's look at question 10. Ten is really about, on some level, missing parameters. Well, not on some level. It's about missing parameters. If you want to determine the equation of this square root function, then you need to determine a, b, h, and k. And since this function is a transformation of root x, and root x has its vertex at the origin, and it has some other key points that look like that, I think it's very valuable to understand, everybody, that a and b do not move the vertex. So whatever a and b are, the fact of the matter is the vertex is still going to be at the origin. Since the vertex ends up being, however, at -3, 4, that means after a and b have been applied, it must have been shifted 3 to the left and 4 up. Now, there are a couple of ways that you can find a and b. If you have some key points, you can think of a and b as being, well, they're related to stretch factors. Okay, so for example, the first observation I make about this blue graph is that it's upside down. And if it's upside down, that's telling me that there's been a vertical reflection. The second thing I notice is that when I look at this vertex, it matches this one, right? It doesn't match. That's not what I mean. They're sisters. One turned into the other kind of thing. Okay? Sister points. When I look at this key point turns into that key point. And I make an observation that the vertical distance between the red point and the green point on the original function is 1. And the vertical distance between the red point and the green point on the transformed function is 1. And I could go even further and say the vertical distance between the red point and the brown point on the original is 2. This is 2. And the vertical distance between the red point and the brown point on the transformed is 2. And what I'm getting at is, since the vertical distances between the points has not changed, I can say that there's no vertical stretch, which means a is -1. I can do the same bit of business now with looking at horizontal comparisons between points on the same function. So this horizontal distance is 1. The horizontal distance between the red and the green point is 1. This horizontal distance is 1. This horizontal distance is 4. This horizontal distance is 4. So nothing's been messed with horizontally in terms of stretches. And now what I have is b is 1. Of course, you have to put these numbers, these parameters into that function y equals a, f of b, x minus h plus k. Is that okay? I don't want to go through all of them, but you would do the same thing here essentially. So I could look at this and say a is 1 because the vertical distance between these two key points was 1, and the vertical distance is still 1. B is 1/4 because the horizontal distance between these two key points is 1, yet the horizontal distance here is 4, which means things have been stretched horizontally by a factor of 4, which means B is 1/4. The graph that I start off with goes towards the sky and towards the right. The graph that I end up with goes towards the sky and towards the right. And that means that both of these numbers must be positive. There's no reflections. Then I would say that h is -5 and k is -3 because that's always the pair of numbers that describes where the vertex is. Other questions? Yeah.
Can you do question 4, numerical response?
Numerical response 4? Certainly. So the thing you have to be careful of here is that you have two functions on this piece of information that you're asked about. This is still related to the diagram at the top of the page. I'll go through it anyway. It'll take a second. And one of the things we'll have to train ourselves to be aware of is when you're writing an exam, make sure you read above that context box. How many questions am I going to have to carry this for? And I think on the Physics 30 diploma exam this semester, there was some that, like, it went on for pages. And then it had, oh, by the way, now use this additional information. So it can get pretty messy. But the thing I want to point out to you is that h of x is a transformation of g of x, which is a transformation of f of x. So we need to transform g of x. We need to focus our attention on the pink graph. And since you're asked about the domain, of h of x, these two parameters are not relevant. And I probably spelled that wrong. And what I mean by that is since the -3 for A is a vertical reflection and a vertical stretch, that's not going to affect the horizontal properties of the graph. And domain is related to horizontal. So if this pink graph is reflected vertically or stretched vertically, or even shifted up 5 units, it's still going to have a domain of x's greater than or equal to -1. The only thing that can change that are B and H. And I just want to check something out here with you. B is 2. Are you okay with that? You see where I'm getting B equals 2 from? Can you tell me what H is equal to? No. We have, yeah, it'd be 4, right? We have to take that 2 and factor it out of the x minus 8. So the bottom line here is that we are going to stretch this point by a factor of 1/2, putting it here at -1/2. Then we are going to shift it 4 units to the right, where it will be at it will be at 3.5. Now, again, it will be reflected and stretched and shifted up or down. So if we want to go that far, it's going to be down here someplace going up. But the domain is still going to be x is greater than or equal to 3.5. All right, let's move on. We are looking at the bottom of page 34. This lesson doesn't start at the top of a page. It's at the bottom of this page. And we're looking today at the square root of a function. Remember that your unit exam is Thursday of this week. I'll draw your attention to this again later in the week, but you can start writing the exam at 8:55 during SABRE support. If you require or are granted accommodation for extra time, you need to send me an email so I have a record of that. You don't need to send me an email every exam, but I need to know at the beginning of the semester so that I can set that up in the library. I'm not trying to dissuade anybody from using extra time, but sometimes in the library, it's not exactly an exam-like atmosphere. There's people coming and going, there's people talking. You know, if you're going to do that, you have to weigh the pros of getting that extra time with having to put up with that noise. Of course, you could wear not earbuds, but you know, noise protection in your ears. The final thing I want to mention about this unit is this is the final lesson we're going to be covering for this unit. There is one more lesson, but in order to avoid having our exam after a 4-day long weekend, we're going to end it here. And at the beginning of the next unit, next week, we're going to start with section 2.3. So 2.3, which is in this unit, will not be on the exam. We need to understand today the relationship between functions f of x and root f of x. What does that mean? It means this. It means if you know the properties of a function y equals f of x, and what I mean by that is you know the equation, you know the domain and the range, the intercepts, maybe you know the graph, what the graph looks like, then what are the properties of y equals the square root of f of x? For example, if I have y equals 3x minus 2, that's y equals f of x. We're talking about transforming this. This is a type of transformation. It's just not an ABHK transformation. Then I'm asking you about this function. And I want to be very clear here, everybody. It's not about knowing the equation of the function so you can put that into your calculator, because you may not know the equation. You may be looking at a graph. And there's a connection here between what the graph of f of x looks like and the graph of root f of x and what it looks like. To begin with, we're going to go through some basic properties of square roots. And you may be a little confused or have some misconceptions about square roots. But the square root of a number can only be found if that number that you're taking the square root of has certain properties. What are you not allowed? Think about that. What are you not allowed to take the square root of? Joel?
Prime numbers?
No, you can take square roots of prime numbers. Prime number would be like 2 or 5 or 7. Square root of 7 exists. It's an irrational number. We'll pick on 3. The square root of 3 is an irrational number. We can take the square root of it. It's just that it's not a nice number to work with. It's 1.73 something, and it just goes on forever. We can take the square roots of prime numbers. Shannon, do you know? Negative. That's the bottom line. You cannot take the square root of a negative number. And the reason is the square root of a number is the number that you square to get what you were taking the square root of. You can't square something and get a negative, which means negative numbers have no square roots. So what we say is the condition here is that the argument of the square root, n, which is underneath the square root, the argument must be greater than or equal to 0. The next 2 points, I'm embarrassed to point out to you that in high school I didn't realize this. I always assumed that a square root would be smaller than the number you're square rooting. And that's true if the number is larger than 1. So if you take the square root of 20, and you could check it out on your calculator. I don't know exactly what it's going to be. It's going to be 4 point something. 4 point something is less than 20. If I take the square root of 100, I get 10. The number becomes smaller. I go from 100, and when I take the square root of it, I only get 10. But when you evaluate the square root of a number smaller than 1, but just a second here. The number is smaller than 1, but it has to be greater than or equal to 0. And I guess what I really mean here is it's between 0 and 1. I should polish up my notes here to say that It's smaller than 1 but bigger than 0. The result, the first time you see this, is kind of surprising. If I take the square root of a number like 0.25, I get 0.5. So I went from something that was 0.25 and I took the square root of it and it got bigger. If I take the square root of 0.057, I get almost a quarter. When you take the square root of a number that's between 0 and 1, you end up with a bigger number. And this isn't just a curiosity of numbers, this is fairly important in what we're doing today. So you can only take the square root of numbers that are not negative, which means they have to be greater than or equal to 0. If you take the square root of a number that's more than 1, then you get a smaller result. And if you take the square root of a number that's less than 1, but between 0 and 1, you get a bigger result. When you take the square root of either 1 or 0, what is it you get? Miles?
1 or 0.
You get 1 or 0. And to just kind of summarize that, we can say the result is invariant. When you take the square root of 1, you get 1. When you take the square root of 0, you get 0. It doesn't change. And we can summarize this. I'm a big number line fan. We can summarize this by looking at a number line that shows different values of n. And below, we can talk about the square root of that. And any number that lies in this region on the number line will not have root n defined. N is defined. Root n, which is in blue, is not defined. Anytime you have a number bigger than 1, you get a smaller result. Anytime you have a number between 0 and 1, you get a larger result. And of course, when you take the square root of 0, you get 0, and when you take the square root of 1, you get 1. Okay, so that was a quick review of the history of square roots of numbers. Let's take a look at an example relating to the topic today. I have a function. The function is f of x equals negative 2x plus 2. And what I've given you is a graph of the function and a table of values. Okay? And I really want you to understand something here. I know that it should be obvious, but these two graphics you're looking at on the screen right now are both saying the same thing. It's just that one is in a graphical form and one is in a tabular form. What does this, I shouldn't have done that. What does this mean? I'll wait for it to catch up. What is negative 4 comma 10 being one of the items that are populating the table? What does that mean? What it means is that that is a point on the line. Okay? What does this mean? Try that again. There we go. What exactly does it mean to say that negative 3 comma 8 is an ordered pair in the table? What it means is that this is a point on the graph. They are telling you the same information. Well, not really, because would you agree the graph is telling you more information? Because the table can't show you every single point. But if I tell you that this table is for a linear function, which I am at the top of the table, then you know that it's continuous from point to point. Okay. So what are we asked to do here? We're asked to write the equation of the function g of x and complete a table of values and a graph of the function y equals g of x. G of x is root f of x. So at the top of your second table, I think I've already got that in there, don't I? Okay. So what I would like everybody to do is I would like you to complete this table of values. I want you to take a minute or two, figure out what the square root of negative 2x plus 2 is when x is negative 4. So what you are doing is you are putting this negative 4 in here and figuring out what g of x is equal to, which is the y coordinate of g of x at that point. While people are finishing this off, I have a question. Is there anybody who filled in that table without using your calculator? You've just learned the point of the lesson. That what you've just discovered is the point of the lesson. You don't need a calculator because, and this is unfortunate that your two tables are stacked vertically. And I thought of trying to condense it in a different way, but then you would lose the graph. If we put these two tables beside each other, I think it's very important for you to understand that this is the y coordinate on f of x. This is the top table. Everything in this column is the y coordinate on f of x. And the y coordinate on g of x is found by taking the square root of the y coordinate on f of x. And after you do this with your calculator a little bit, if you put negative 4 in for x here, you're going to take negative 4 times negative 2 and add 2, you're going to get 10. Which means that this y coordinate is negative 10. I'm just curious, Will, when you did this, did you do it once kind of on paper and then you saw what was happening? That's almost always the case. If I put in negative 3 for x here, what would I get? This one was g of x equals the square root of negative 2 times negative 4 plus 2, which was root 10. And that's probably where Will and a couple of other people went, oh, well, of course it's root 10 because that thing underneath is 10. Over here, we would have g of x, g of negative 3, but I'm just going to call it g of x, is equal to the square root of negative 2 times negative 3 plus 2. And you would work out what this is, and you would discover that this number under the square root is 8. And that shouldn't be a surprise because negative 2x plus 2 is 8 at that point in time. And when I said that that's the lesson, I'm maybe over-exaggerating a bit, but that's really the big part of it is when you take the square root of a function, you simply take the square root of every y coordinate. That's it. So this will be the square root of 6. This will be the square root of 4. This will be the square root of 2. This will be the square root of 1. This will be the square root of 0. And this is not defined. Anything past that point is not defined because when you put those x coordinates in, you'll have a negative number under the square root. Some of these, of course, can be simplified. I don't want to spend too much time today on simplifying radicals, but at the very least, you should understand that root 4 is 2, root 1 is 1, and root 0 is 0. Root 8 is 2 root 2. From Math 20, you can decompose, I don't know if that's the right mathematical word, you can factor 8 into 2 times 4, so root 8 is root 4 times root 2, and root 4 is 2. So this is 2 root 2. I want you to notice that this point is the same on both graphs. It's invariant. And this point is the same on both graphs. It's invariant. Why? They're both invariant because they have y coordinates that when you take the square root, you get the same y coordinate. They're invariant because that's where y equals 0 and where y equals 1. And now if we start to piece this together, if I go to my graph, that means, and I'm going to end up blowing this up, but I want to take a look at the whole graph to begin with, that this point and this point are invariant. And I really want you to focus on this idea. The reason why these 2 points are invariant is that this is where y equals 0 and this is where y equals 1. Any place on an original function that has a y coordinate of 0, in other words, it's an x-intercept, or any point on an original function that has a y coordinate of 1, those will be invariant. Any place on an original graph that's below the axis the square root of that portion of the graph will not exist. Because every place the original graph is below the x-axis, has a y value of negative. Well, it's negative, and you can't take the square root of a negative. And as I've already explained, the square root of the function will be the square root of the y coordinate. Every point is going to have a y coordinate that's square rooted. What that tells you, everybody, is that the domain of the square root is only going to be the region of the graph that is either above the x-axis or on the x-axis. We could even write that in. I don't want to do it right now, actually. A second, change my mind. But the domain of the square root of the function will be x is less than or equal to 1. Because those are the only places that have positive or 0 y coordinates. Now, I'm going to go back to my regular viewing. So we have those 2 points. And if I were to take, let's do the mapping first. It says, what's the mapping that occurs? From y equals f of x to y equals root f of x, the mapping is this. That's it. That's what happens. Take every point, rewrite the coordinates, but you use the square root of the y coordinate instead of the y coordinate. So, for example, looking now at the graph, if I were to take on the original function, let's take this point on the original function. I'm going to use green for the original points. This point is at -1, 4. Well, if it maps to x, root y, then it's going to become, and you're going to have to decide how you're going to write all this down. I'm just in a teaching mode right now. It's going to become, on the new graph, -1, root 4, which of course is -1, 2. But listen, visually, all that means is that this point here, with a y coordinate of 4, is now going to have a y coordinate of the square root of 4. And 4 is a number bigger than 1. The square root of it is a smaller result. We started the lesson off with that. If I were to take a look at this point, just to pick another point that I have access to, this point is at -3, 8. It is going to map to -3, root 8, or -3, 2 root 2. And if you use your calculator and evaluate what 2 root 2 is, it's going to be very close to 2.8. But I would like you to do so just to make sure you know where I'm getting 2.8 from. 2 times the square root of 2. Was I right? And that's kind of a benchmark for where we can draw that. This is 3, this is 2, 2.8. I'm just going to fall down to about 2.8, which will be about here. Of course, if we were to write with a label the y coordinate there, you wouldn't put 2.8, you'd go to root 2. Right? We want to be exact. All right. I mean, we could certainly do more. This one is, I'm not going to write this down, but this one is at negative 2 comma 6. What is the square root of 6? I'm going to go out on a limb and say it's 2.3. So 2.4. Would it round to 2.4? Is it 2.44 something?
Yeah.
So be careful. Don't round it to 2.45 and then round it to 2.5. If it's 2.44, you're going to round it to 2.4. We're picking nits here. That's not the point of the lesson. So that one would go from this point here down to a y coordinate of the square root of 3, which is about 2.44, whatever the number is. Let's take a look now, and I'm drawing these points awfully big just so that they come out well in the video and you can see them. Let's take a look now at this point. And I'm just going to arbitrarily put it there. And in decimal form, ask you to estimate in your head what the y coordinate of that point is, that green point on the original function. And I don't think I would have a problem if anybody said 0.3 or 0.4. Let's say it's 0.35. And I don't really care what the x coordinate is because as all of these other transformations indicate, what happens is it's only the y value that changes. So I don't care about the x coordinate there. If the y coordinate is 0.35, then it will map to give us a new point of some number times root 0.35. And I can't cope with square roots of decimals like that. So I'm going to go to my calculator and I'm going to change calculators. I just don't like this one. The square root of 0.35 is 0.6. Oh, it's bigger than 0.35. It's gone up. So when we replot this point, it's going to be higher than it was before. So the pattern here is an important one, that this point and this point don't go up or down. They're invariant. Any points over here to the right, any points over here will fall because they all have y coordinates greater than 1, and when you take the square root of a number greater than 1, you get a smaller result. Any points, this is getting pretty condensed, any points in this region here are going to rise because all of those y coordinates have y values that are between 0 and 1, and when you take the square root, they get bigger. So what this graph looks like is that. And this little bubble, this part, I'm going to just adjust this ever so slightly. Close enough. This little bubble where the red graph goes above, and I didn't hit this point well, but it should go through that point. That little bubble where the red graph is above the original graph is important when you draw these. All right, have we answered everything about this question? What does it ask us to do? Write the equation of the function. That was already done for us. We've completed the table of values. We've graphed the function. The mapping we've taken care of. If you wanted to write out the domain and range, it's pretty obvious by looking at it. Let's turn the page, please. So now we're going to look at some quadratic functions. And these functions that we draw the square roots of don't have to be quadratic. But the point I want to make to you is you don't know the equations of any of these graphs, so you can't use your graphing calculator. And it's a mistake. It's a horrible mistake for you to try to figure out what the equation of these are. Okay. The first thing you're going to do is say that any place y equals 0 or y equals 1 will be invariant. So this will have 4 invariant points. Any place the graph of the original function is below the x-axis, the square root of the function can't exist. Because remember, we're taking the square root of y coordinates, and everywhere in between those two solid dots, you have negative y coordinates. What I'm telling you is that this down here, this is the domain. I don't know what these numbers are, okay? But if this number was 0.2, then I would say x has to be greater than or equal to 0.2. And if this number were negative 1.8, I would say x also has to be, or can be, less than negative 1.8. But what I've drawn at the bottom is a domain statement. Your range, of course, will be that y is greater than or equal to 0. Because if the two arms of that parabola go up to infinity, you're going to be taking the square roots of larger and larger numbers. You're still going to approach infinity. Don't say you're going to approach the square root of infinity, because infinity doesn't work that way. What does the rest of it look like? Listen, if we wanted to, we could do this. Please don't. We could just say, well, I know it's going to look like this. Except you probably want to pick a point or two to get the right shape. And I'm just going to leave that up there, even though I don't want you to draw it. I'm going to take this point right here on the original function. It has a y coordinate of 3. What is the square root of 3? I think it's 1.73. So this point falls to here. And my curve doesn't go through that point. So I didn't do a stellar job of drawing it. What I should have drawn is something closer to that. And I could do the same thing on the other side and get rid of these, which, and I told you don't draw those, right? I didn't want you to, because that was just, what's the word? Well, I drew those without much thought. Okay. And in fact, when I look at this thing, the one on the right should probably be a little steeper, but so be it. Is that good? Okay. What about this one? Well, any place y equals 0 or y equals 1 will be invariant. This function is going to have 2 invariant points. Any place the original function is below the x-axis, you cannot take the square root. But this function is above the x-axis everywhere. So if I were to draw a line indicating the domain, And I want to back up. When I said this is the domain, I mean that. It's the domain of the square root. It's not the domain of the original. And when I say it's the range of the square root function. I often, harp on the idea of being precise in the language. At least I do in my head. So just saying domain is not good enough. We've got two functions going on here. But since the original function has y coordinates that are positive, or the original function has y coordinates that are square rootable everywhere, the domain of the square root function will be any real number. The range, of course, would be, well, we'll get to the range in a second. Would you agree that every point above those two red points on the original function is going to fall, and every point below is going to rise? So do some quick calculations. Would you say that this is 0.5? It's not exactly, but 0.5. What's the square root of 0.5? I'm not asking you to do it in your head. Just on your calculator, what's the square root of 0.5? Sorry, caught you off guard. Oh, I know this one, 0.707. 0.71. So this is going to rise. I know that because of trigonometry. Okay? And you will learn that too. That's going to rise to that point. You could, take some other points here like this one, which is at 3 for a y coordinate. The square root of 3 is 1.7 something. Just putting these extra points provides a little bit more texture to your diagram. It provides more detail to the diagram. So what this is going to look like is this. By the way, this is not a parabola. You don't want to call it a parabola. It looks parabolic, but it's not. It's a different kind of shape. So your range would be y is greater than or equal to whatever that new y coordinate is. 0.707, if that's what it was. Will this function have any invariant points? How many invariant points? Miles? 1. The only invariant point will be here. And every other point on the function is more than 1 for a y coordinate, which means the square roots will make every other point fall closer to y equals 1. Again, if I pick on this point, which is 2, pardon me, that point has a y coordinate of 3. The square root of 3 is 1.73 approximately. It will fall to about here, and the same on the other side. This point here will fall to root 3, and that gives you a little more detail, and it's going to look like that. The key is invariant points. Points above them fall, points below them move up. Any invariant points, everything is going to change. Can we take the square root of the function everywhere? Yeah, because none of the y coordinates are negative. So if this is at, I'm going to just do some approximation, and Joel, you're close to me so I can hear you well. You're going to be my calculator guy. If I say that that's 1.8, then that new y coordinate will be the square root of 1.8.
Which is 1.3.
So it goes down to about 1.3. We'll just do the 3 thing again. This is 3 and 3. The square root of 3 is 1.7. Approximately, we get a fairly decent picture of what this thing would look like. Will this have any invariant points? How many invariant points? 4. Excellent. It's going to have an invariant point here and here because this is where y equals 0. It's going to have an invariant point here and here because this is where y equals 1. The domain of this function will only be indicated by that. Because outside of that domain, to the left of that I've indicated at the bottom of the page, y is negative, and to the right, y is negative, so you can't take the square root of a negative. Every point here is going to fall. Every point in here is going to rise. And I immediately regret doing that in red, but I'll draw the new graph in a different color. Okay. If I take this point, which is at 2.7, Joel, what is the square root of 2.7? 1.6. You had that all ready to go, eh? 1.6, it's going to fall to about 1.6. You know, I think that's good enough. I'm going to erase those little arrows. I think that's good enough because I know that in the middle it falls, and in between the invariant pairs of invariant points it rises. So this is going to go up. It's going to bubble up and go through that point. Looks something like that. And unless you're doing this with a graph that has a series of straight lines, that's as good as we can hope for. The range would be from 0 to whatever the square root of this vertex is. If that vertex is at, I'm just going to say, Q, that would be the range. F, 3 invariant points, 1 here, here, and here. I don't think we need to pick some points here because there's really not much of an option. When we draw this, it has to go up, but then it has to go through that point. It has to be above the original function. That's what it looks like. Range is from 0 to 1. Domain is, well, from whatever this x coordinate is up to and including whatever that x coordinate is. Two invariant points, here and here. I think whenever there's a maximum value or a minimum value to something, I think you need to relocate that point precisely to find out how big the maximum or minimum is later. So I'm going to say that this is at 0.6. Y coordinate of 0.6 is going to be the new location, which is 0.8. So it rises a little bit. And that means that this is what the graph looks like. And you could certainly determine the domain and range from that. Again, the new function. What I've written in brown here is y equals the new function root f of x. It doesn't exist wherever the original function was below the x-axis. It only exists where the original function is either on or above the x-axis. What will the square root of this function look like? It'll just be a dot. can you live with the fact that this function that we're looking at here could be this? I mean, I'm not saying these squares are 1, but if this vertex of the original function is at 1, actually I'm wrong. I need a negative in front to flip it over, don't I? Okay. So that's the original function. I want to show this to you on your calculator. I'm going to graph negative bracket x minus 1 n bracket squared. I'm going to go zoom 6. There it is. Okay. I'm going to zoom in a little bit here. Okay, and now I'm going to do a couple of things. I'm going to, for y2, graph the square root of that function. And I'm going to do that not by retyping it in, but going to vars, y vars, and choosing y1. Now, I can't prove anything to you if I hit graph right now because the old one is still there. I don't want to get rid of the old one because then y1 has no reference to it. But if I go to the equals and I hit enter, I turn it off. I don't know if you knew you could do that. So now when I graph it, the other function is gone, but it's graphing the second one. The problem is you can't see that point, can you? But if I go to my format, I can turn the axes off. These are things that you probably wouldn't do. And I'm going to go zoom decimal just because, cross my fingers. Yep, there's the point. It's there. Don't worry about all the details of how I had to get the zoom settings and display settings right. There is a single point there. I'm going to draw the square root of this function without even touching the smartboard. Done, right? Because everything is below the x-axis. The square root of the function doesn't exist. Any ideas on what this looks like? And the first time I saw this, it wasn't what I expected. It really wasn't. And then when I thought about it, it made sense. I mean, these 3 points have to be invariant. Any idea? Miles?
It comes to a point at 0.
Can you enhance on that a bit? Can you show me what it would look like by drawing it? No. That's kind of what I thought. I kind of thought it would do that. What we're talking about here, and I thought the same thing. I thought it had to do something like this on both sides. It doesn't. Any other ideas? And again, if anybody gets this, I'm blown away because it's a really tricky thing. Yeah. It's an absolute value function. It's going to be a series, not a series, it's going to be 2 straight lines. Of course, they go on forever. I don't think that's something you need to know. It's just a curiosity thing. It becomes apparent because if you have y equals on the original function, y equals, say, x minus 1 quantity squared, and you take the square root of that, you get plus or minus x minus 1, which is plus x minus 1 and minus x minus 1, which is a series of 2 lines. All right, we have one last example. Graph the function. Well, it doesn't even say graph it. What's the domain and range of the square root of this function? Let's graph it anyway. Are there any invariant points? Say there's a whole slew of them. Can you count how many invariant points there are? Well, whole slew is an exaggeration. 3. You're on a roll today. That's right. 1, 2, 3. Will the square root of the function exist anywhere in this region, generally speaking? No. Will the square root of the function exist anywhere in this region? It's a bit of a trick question. Will the square root of the function exist anywhere in that region I've indicated in green? No. Because the function doesn't go over to here. The function ends. There's no arrow on there. So it's only going to exist here. Green means yes, red means no, which doesn't really match the colors that I'm using for the points. But the bottom line is root f of x won't exist in this region. Root f of x will exist here. Just briefly, this has to fall to 2. That the vertex, that peak, that summit of that little mountain has a y coordinate of 4. The square root of 4 is 2. This has a y coordinate of 2. The square root of 2 is root 2, which is 1.4. We know from experience this will have a curve to it. I don't know if this next part is really going to ring true or make sense, but how many of you understand that the curve here is more severe than the curve here? Like intuitively, it makes sense. The reason is the curve that I've labeled as 1 comes from a straight line that's steeper. So the y coordinates are going to be changing quickly, more quickly. That's almost a calculus idea here. So what is the range? The range is y. There's a minimum and maximum y. The lowest y is 0. The biggest y is 2. What is the domain? The domain would be x equals -10 and 2 is less than or equal to x, which is less than or equal to 6. On page 86, 2, 3, 5, and 6, and then there are some multiple choice questions. This deals with the square root of a function. Tomorrow you will get a couple of review handouts. One of them, we will just spend a little bit of time tomorrow going through the content to remind you of everything that we've learned. The other one is a series of roughly 60 multiple choice and numerical response questions. Might not be 60, might be closer to 40. And those will give you an idea of what types of questions you will see on exams, because what the types of questions you learn with are generally a little bit of a lower kind of level of understanding. But by the time we get to the exam, the length of that pendulum is shorter and we're at a higher level. Okay, so we'll take a look at that tomorrow. In the meantime, you have about 15 minutes left in class today.